All right, today we are going to introduce a specific type of amplifier that's very important called the operational amplifier. My name is Vivek Subramanian.
And I'm Michel Maharbis. Let's get started. So operational amplifiers, or op-amps, have been around a long time. In fact, the original idea for an op-amp really dates to the era of vacuum tubes. In the World War II period, an engineer at Bell Labs named Carl Schwartzel, Jr., really came up with the first idea or the first embodiment, I would say, of one of these things. Now, when integrated circuits came to be in the 50s, at Fairchild, late 50s, you started to see monolithic integrated circuit op-amps, in other words, op-amps built into silicon. And from that arose the 741. So the 741 is this sort of classic op-amp that most electrical engineers have heard of in their schooling. And it was really sort of the canonical op-amp for a very long time. You can still buy 741s. Yeah?
So it's worth noting that the 741 is just a number. I don't know why they chose to call it the 741. It was just in their catalog as a 741 or something like that. I mean, 741 has no technical meaning.
Okay, I see. Okay, well, I actually have to be honest, I don't know why it's called the 741. There's probably a very cool historical detail that somebody can look up and inform us about, maybe. But anyway, the point, though, is that this thing really set the stage. And many other op-amps since then have adopted the same configuration so as to essentially be compatible with this same op-amp, the 741. Okay, now, op-amps are basically high-gain amplifiers. We're going to go into that in a minute. We're going to spend some time going through why they're purposefully made to have incredibly high gain. But the more important thing, I think, to differentiate it to what we just discussed in the last module is that they have differential inputs. So let's look up here at the op-amp circuit symbol. You'll recognize right away the plus and minus supply rails and the output terminal. But what's most relevant is that the input is actually differential. In other words, there isn't an input terminal that's referenced to ground. There are two, right? One that's got a little positive sign, one that's got a negative. We'll come back to that in a minute. But as a preview, what's essentially going to happen is that the output voltage is going to be determined by the voltage across V plus and V minus. In other words, V plus minus V minus. It's the differential between the two, or the voltage across the two. And the internal gains of these things can be very large. I mean, in the millions, okay? So it responds with a very reasonably high voltage, even to very small signals. Just think about what millions means. A microvolt would give you a volt, right, to give you an idea. And they're absolutely ubiquitous. Op-amps are used as low-cost components for, applications all over the place. You probably would find op-amps in many sort of household things if you were to look around and pop them open.
And if we look at those op-amps, you'll again recognize when we draw them in schematic form that again you see a triangle, just as we had in our amplifier section from the previous time. But of course this time we have plus and minus inputs, which we call specifically the plus input is referred to as the non-inverting input, and the minus input is referred to as the inverting input. You'll see why when we talk about what the gain actually works out to be. There's one output, however, in this case, and that's this output here. You'll also notice that we've got some numbers. Those numbers are the pins on an 8-dip pin package.
For a 741.
For a 741. If you were to go and buy a 741 at the store, at Radio Shack or the like, you bought an 8-pin version of it, you'd find pin 2 is always the non-inverting input.
Well, pin 2 is the inverting input.
I apologize. Pin 2 is the inverting input. Pin 3 is the non-inverting input. Pin 6 is the output, and so on.
Now, I think Vivek was hinting at this with the number earlier, kind of joking, but there are myriad op-amp designs. We picked the 741 because it's so canonical, and we thought it might be fun to kind of ground it in reality and show you what the dip is. But certainly, this is like not the only op-amp by far. There's many technologies of op-amps out there. But anyways.
That's right. And interestingly enough, though, a lot of the newer op-amps have tried to stay pin compatible with the 741 just for convenience. Mm-hmm. And so when we draw a schematic, what you'll again see a lot of similarities to what we had before. You have a plus supply voltage, which we call plus VCC, a minus supply voltage, which we call minus VCC. There's a ground reference, and then you see that we have inputs and the output. Commonly, when we will draw circuits, we'll often draw it without showing the power supply. We just sort of assume that the power supply is there.
Makes sense. Okay. So Before we go on and talk about the equivalent circuits, we also thought it would be kind of fun to show you what the insides of a 741 might look like when you populate it with what's really in there, with the transistors that are really in there. So each of these, if you look at this, we're not expecting you to make heads or tails of this, to be honest. It's really just a little bit for fun. But if you look, each of these is a BJT. Remember we talked about NPN and PNP BJTs at one point? So each of these is a transistor. You also see resistors that are used to set biasing and a capacitor here. But you do see that there's the non-inverting input, like we said, the inverting input and an output here, and then the supply rails, V plus and V minus. The offset nulls are used to essentially offset little changes that there might be in the voltages, and we'll leave that alone for now because it's not a really big deal. But you can see that what we're about to do is come up with an equivalent circuit that's linear. It's a linear equivalent circuit. We're going to show you how to use it and how to solve for problems that involve the op amp and let you design things. But we're never going to really refer to this again. We're just not going to worry about what's going on inside.
That's right. So in this course, what we are going to do is we're not going to worry about the internals of the op amp. But by the time you're done with this course, you're still going to be able to analyze or design circuits using op amps.
Right, and that's, again, we keep hammering this over many modules, but that's the beauty of modularity and equivalent circuits. You do not need to know what's in here to go off and design very useful op amp circuits and even amplifier circuits in the context of some integrated circuits. Anyway,
that's right. Okay. All right. So Michel's already told you that the gain of an op amp is one of the important characteristics of an op amp. And in particular, op amps generally have very high voltage gain. Michel also told you that op amps have these differential inputs. In other words, a non-inverting input with the plus and an inverting input with the minus. The gain, and specifically it's what we call the op amp gain or the open loop gain. You'll see what open loop means in a little while. The open loop gain of an op amp is calculated by this equation shown here. In other words, the output voltage VO is equal to A, where A is the open loop gain, times the difference between the non-inverting and inverting input voltages. In other words, VO is equal to A times VP minus VM.
As a quick little experiment, if you were to ground Vn, you would get essentially an amplifier that works very similarly to the amplifier we did in the last module.
That's right, because Vn would be 0 now.
Right, and A would have the same function that A had in that last module.
Correct. Now, this equation is again limited in the regime in which it applies. So here we see a plot of the dynamic range, which you've seen before, and you see that there's a window close to the supply rails over which the output can swing, which means there's constraints on the input. Now this latter point is kind of interesting. If we have a really, really high gain, it means the input window will be really, really small.
That's true. It's going to be really tiny. So hold on. Let's just do that experiment. I think we did it a couple slides ago. But if V out is a volt and my gain is 1,000,000, that means that the difference between the inputs is a microvolt.
Correct.
It's a microvolt.
Correct.
Wow, that's really
and
tiny.
by the way, the gain number you mentioned is not outrageous. Most op amps that you would buy commercially are spec'd to have a gain of at least 100,000.
Wow. Okay. But that's weird. That means that we don't have a lot of range of the input. Our dynamic range is pretty low. I guess we're about to discuss that.
That's right. We'll figure out how we use that.
All right. Let's see what we got in store. So, what does the inside look like? What kind of equivalent circuit can we put together based on what we've told you, not just in this slide module, but in the one before? So, sort of building on what we've learned, we're going to reuse a lot of the same ideas. So, our op amp will have a input resistance R sub I that exists between the non-inverting and the inverting terminal. Okay, that's one thing to know. The voltage across this resistor is Vp minus Vn, obviously, just by looking at it. And the op amp will have a voltage-dependent voltage source that multiplies that difference, Vp minus Vn, that's across this input resistor, by the open loop gain, or the internal amplifier gain. And that voltage will be presented on the node right before this output resistor. And again, then that gets connected at the very output to some load resistance.
Now, before we go through values, just to show you Michel's inadequacy in his previous example, let's mock him a little. So you remember he gave us a circuit with a gain of 10, an input resistance of 1 kilo ohm, and an output resistance of 1 kilo ohm. Let's look at what a decent amplifier would have.
You must be really mean in class. Okay, so let's look at this. So the open loop gain of a typical op amp is somewhere between 10,000 and 10 million or 100 million. So it's huge, right? I mean, the gain is absolutely huge. And again, reference what I said in the last slide where you're like, wait a minute, that means a very tiny input generates this monstrous output. And before we even talk in the next slide of what we're going to do, these op amps are not going to output megavolts, right? So there must clearly be some other reason why this gain, is so large, and there must be something else we're going to do to this circuit. The input resistance, following Vivek's suggestion to kind of compare, is higher than 1 million ohms, right? Mega ohm, and this is
10
immense.
teraohms.
It's 10 teraohms. Wow, compared to my 1 kilo ohm, I feel pretty inadequate. And likewise, I had put a kilo ohm, and that's huge compared to an ohm, maybe 100 ohms for some of these, but an ohm. And the supply rails are a handful of volts up to tens of volts. But look, and the key here is look at how much closer it is to an ideal op amp than the things I chose in the last module, right? We want the open loop gain to be infinity, and we'll tell you why in a minute. You want the input resistance to be infinite and the output resistance to be 0. Okay, so keep that in mind, and let's think about how we're going to deal with this.
All right. So to think about how we're going to deal with this, remember the problem that Michel's already alluded to. In other words, we have a huge gain, and we have a limited supply voltage. That being the case, the dynamic range on the input is going to be tiny. We would normally be limited to an input signal of a few microvolts. However, it's worth noting that we have a way of dealing with this. And additionally, we can deal with this to get around some other problems. In the previous slide, Michel showed you that the gain could be 10 to the 4 to 10 to the 8. That's a huge spread.
I didn't think about that. Right, the spread is very big.
Right, and it turns out gains are really poorly controlled. If you took an amplifier and you measured its gain at room temperature or several degrees above room temperature or a few degrees below room temperature, the gain would vary quite a bit.
So that's interesting. So in little op amp, from op amp to op amp, and even within an op amp, as the temperature varies in a normal room, the gain is wobbling all over the place.
Yeah, that's right. Within a single op amp, it's all over the place. And worse still, I can buy 3 op amps from the same batch, from the same manufacturer, that are supposed to be nominally the same, and from part to part, there'll be a huge variation in gain. So the point is we have two situations. One is we're limited in dynamic range, and 2, gain is really poorly controlled.
Okay, so let's talk about feedback. So what we've done is we've taken the op amp. It's in this dash box right here. This is the op amp model we showed you before. The only little wrinkle is that we are going to ignore the output resistance here. It's no big deal. The analysis would work just fine with it. It's just to make everything a bit simpler. And we're going to connect an input source with a resistor here to the inverting terminal. Okay, and we've got the non-inverting terminal grounded out. Now there's one big difference. There's some connection. There's an electrical branch that goes from the output node to the inverting input node. You see that? And there happens to be a R2 resistor. When you see this, you can see immediately that something about the output signal is being used to modify one of the input signals. Okay? This might be, I don't know, it might be weird to you at first because it seems like we're subtracting something about the output from the input, but it's going to actually work really well in our favor. This concept is really powerful. It's a subset of a much broader concept called negative feedback, which is used in all sorts of control systems. And in this case, we're going to use a resistor, but later on in this class, we're going to see what happens when we put more complex components in the feedback path.
And if I understand correctly, you said we're subtracting, and you called it negative feedback. And you're saying that because we're connecting the output back to the inverting input, and the gain term in the inverting input has a minus sign.
Oh, actually, that's a really good point. I'm glad you brought that up. So, and I overlooked this. So it's absolutely true. It's negative feedback because you're going from the output to this V minus terminal, right, the inverting terminal. Had we been doing it to the positive terminal, you could have a condition where it's positive feedback, which is absolutely not what we're talking about. And that leads to very, very different results. So negative feedback is going to serve to essentially stabilize, even though I haven't defined that, it's going to serve to stabilize the output and control our gain.
And that's because of that minus sign in this equation.
That's right. That's exactly right. Okay, so let's start by writing KCL at the input node. All right. Now you might wonder, why are we doing this? Well, it's because we've got a new current that's feeding into the input now. Okay, it happens to come from the output, so it's obviously going to relate the two. So let's do KCL here, and this is very easy, as we've done before. We're going to do a KCL at each of the 3 branches. Okay, so minus V minus V0, V output, sorry, divided by R2, right? That's this current going down this branch. V minus divided by R in is the current going down this branch, because obviously the other node is grounded, so it's V minus minus ground, right? And V minus minus the source voltage Vs divided by R1, that's the current going down this branch. And all of those exiting currents must equal to 0. Okay, that's KCL. Now I'm going to rewrite it before handing it over to Vivek. I'm going to rewrite it in terms of conductances instead of resistances. And so what I'm going to do is it's exactly the same thing you just saw a minute ago in terms of the voltages, but I've gone from R2 to G2 and R in to G in and R1 to G1. That's, remember, G is 1 over R. Just so we don't have fractions and we can make the next slide a lot easier to just sort of parse. So picking up here, Vivek, we've done KCL at the output node, and I'm going to leave that there for you. What else should we do?
All right. So we've got that equation now written in terms of the conductances. Let's go ahead and start thinking about what each of these elements means. In particular, we've got everything in terms of the output node, but if we look at V minus, we know that there's a relationship between VO and V minus. In particular, we know that VO is going to be A times V plus minus V minus, but V plus is 0. So therefore, we can say VO is equal to minus A times V minus. So we've therefore got a relationship between VO and V minus, so we can take this equation here, and every time we see V minus, we can replace it by minus VO over A. And so what we've got then is our equation over here becomes this equation over here, where every time we saw V minus, we replaced it by minus VO over A. I'll also point out that because A is very large, you'll recognize that minus VO over A is a really small number. So keep that in mind.
So conceptually what you've done is you've kind of combined 2 constraints that exist between the output and the inverting input. We did a KCL at the input node, and that told us something about that feedback loop. And of course you knew that the output is dependent on the input by V out equals minus A times V minus. So you combine those 2 constraints, and my guess is you'll be able to show how the feedback loop affects the gain. Is that fair?
That's right.
Okay.
Okay, so we've got this equation set up. Now, let's actually start putting in some numbers. Okay? So to do that, let's go ahead and write an expression for VO over VS. That's going to give us the gain of this overall circuit. All
okay,
right?
So that's the gain of the op-amp plus its feedback loop.
Correct. That's
okay.
the gain of the op-amp plus the feedback loop, and,
okay.
and includes this resistor R1 in our analysis. Okay? And what we've got is VO over VS. We can solve just by taking this equation and rearranging to isolate out the VOs and isolate out the VS. And we get VO over VS takes this form. Now, this is the form we have. Let's take advantage of the fact that we have values for all of these. We know what A is. We know what G1 is. G1 is just 1 over R1. We know what G2 is, so on and so forth. We can go ahead and plug in some numbers. If the gain is very large, we can simplify things even further. Because if the gain is really large, then A and A plus 1 are approximately the same thing, part 1. And part 2, this term is going to completely outweigh all of these terms because of the very large gain. Okay? And so this equation is going to simplify. Numerator stays unchanged. It's minus A over G1. Denominator, 2 steps. First, we can ignore the G in and G1 terms, and we just have G2A plus 1. And then A and A plus 1 will be approximately the same if A is a really large number. So we get a really interesting result. The effective circuit gain of this circuit is now minus G1 over G2. Given that we know that G1 and G2 are just 1 over R1 and 1 over R2, we can say that the effective circuit gain, VO over VS, is just equal to minus R2 over R1.
Wait a minute, but this is really weird. First of all, it put a minus sign on it, but I guess that's not, doesn't bother me too much. But wait, you're telling me that the gain of this whole circuit in no way depends on the gain of the op amp?
Right. I'm showing you two interesting things. One, you're right, there is a minus sign, and the reason for that is we're applying our input signal on the inverting input.
Oh, okay.
So
okay.
it shouldn't be surprising that there's a minus sign because there's a minus sign over here as well.
That's right.
Okay?
Okay, that makes sense.
But you are right that we got a really interesting consequence where we saw that the gain of the circuit no longer depended on the gain of the op amp, assuming
it's large.
the op amp gain is large.
That's right. It doesn't matter if it's 1,000,000 or 1,010,000, you'll pretty much get this
Right.
behavior, but it's got to be big.
Right, because this is the case where we haven't made that assumption. So here the gain does show up in the equation. But the moment A becomes large, we get to this case where the gain no longer matters. Now, this has a big benefit, Michel. Maybe you can talk about that.
Yeah, sure. I mean, I think I see right away. Why is it a big benefit? Well, you don't have to worry about variations in device or variations in temperature. It also means that we can use, we can buy an op amp and we can just pick external components and set the gain we want and change different circuits will give us different gains with the same op amp. So, in other words, I guess I hadn't thought about this till now. Wait, that's not true, but I can pretend I haven't thought about it till now. You know, you would otherwise have to buy an op amp for every individual gain if you didn't have this, right? I'd have to go to the store and I'd have to have a 10 gain op amp and an 11 gain op amp. Here I've got one op amp, it's got a monster gain, and I just use resistors to set the circuit gain.
That's right. So you had two things. One is you now get to pick your gain, which you're right. And then the second thing is you said you don't have to worry about variation. That's a key point because resistors you can buy with resistances guaranteed to actually fractions of a percent today, no problem. And they change with temperature, but they're pretty stable. They don't change a whole lot with temperature. Contrast that to the op amp, where I said the gain could vary from 10 to the 4 to 10 to the 8.
Right.
So I can get much better control.
And I can see all sorts of other things, like maybe I replace this resistor with a variable resistor, and now I have this thing I can tune, I get different gains. Huh. Okay, maybe I start to see this. So I guess feedback must have a sort of a lot of different interesting advantages. So I guess what is this?
So what we've got there is I've got sort of a canonical representation of a feedback system.
Okay.
What I have is on the forward path, I've got some sort of function that relates my input to my output. Okay? And I've called it A, where my input is SI and my output is SO. If that was the op amp I was looking at earlier, that represents the forward path gain of the op amp. Okay?
Okay.
Which would be very large because that's just the op amp gain. And then I have a feedback path which sort of is sampling my output and feeding some fraction of it back to the inverting input. Okay? So I'm doing a subtraction here. That's what this negative sign indicates. In the case of the op amp circuit I looked at before, that just represents the effective impact of that resistor. So this is a canonical representation of a feedback path. As of right now, you can just use the version we looked at in the previous slide, which is you got an op amp in the forward path and a resistor in the feedback path.
You know, this little drawing here is in a sense to try to motivate those of you that find this compelling to go off and take control courses and think really about control. This representation is a very basic, control 101 type of notion that the output state of something depends on some function that looks at the input, but also looks at the output or some permutation, some feedback of the output. In this case, it's negative feedback. So if this kind of thing floats your boat, I would say definitely look into taking some control courses. There is centuries worth of wonderful consequences for this, and it absolutely has to do with modern everyday issues from automated cars to airplanes to the things that control temperature in your house.
And when we start talking about frequency response later in this set of modules, you will also come back and visit this a little bit.
Yeah. So these 2 points here, I think we've already made in that those two resistors really set the gain. It's very nice. It can be made very precise. It really won't be sensitive to temperature, and the internals of the amplifier, as long as A is large, don't play a huge role. But the last point, this one here, is new, and it's a good point to remember, again, in the context of maybe a greater exploration of control. What we did here is we sacrificed gain. Remember, our internal gain of the operational amplifier is like 1,000,000, okay? But we really don't need that. Maybe we need a gain of 10 or a gain of 15 in a normal device. We sacrificed that monster gain to achieve something that is more robust. that is more stable, if you will. And this is one of the advantages of using feedback, in particular negative feedback, and it's used in many, many contexts. This idea of sacrificing this gain to an advantage, in this case robustness or stability, is a really big deal. And it's important to see why. Now I think you can see why op-amp manufacturers happily make op-amps with a gain of 1 million or more, even though their precise control of that gain is not that good and is also unimportant, right, once you know how to do this.
Okay, let's do it. So here what I've got is I've got an op-amp circuit. And the op-amp circuit, again, I've included the internal input resistance of the op-amp. I've got that dependent source gain element. And now I've got an output resistance in here, RO. So I'll provide those values for you. I've got a gain of 1 million. I've got an input resistance of 10 mega ohms. And I've got an output resistance of 10 ohms. So that seems like a pretty nice looking op-amp. And I've got a supply voltage of 10 volts. And here I'm doing a slightly different circuit topology. I still have a feedback path. So I do have a resistor between my output and my inverting input. So I have a negative feedback path. But now I've done a couple of different things. One thing I've done is I've got a resistor from the inverting input to ground, R2, and now I'm putting my input on my non-inverting input.
Okay, so I think this makes 2 points. The first one is we've still got feedback only to the inverting terminal. So it's still negative feedback. And in this class, we're really, if you don't have that, you should be suspicious. You probably made a mistake. But the second point is the one Vivek alluded to. I think it's very important. There are many different negative feedback combinations with resistors in various places and so on. We're just going to explore another one. And then we're going to get into lots of different combinations in the next module that give you variations on the theme that have different advantages and disadvantages. So don't be worried that this is different from the 1-2 slides ago. That's the point. Once I know negative feedback, I can do all sorts of combinations of resistors and other components to get what I want.
And the beauty of the way we're dealing with these op-amps is we're showing them as these idealized equivalent circuits. And with these equivalent circuits, you can ignore that it's in a triangle. You're essentially solving it just like you would solve a regular circuit. You get to use KVLs, KCLs, doesn't matter. You don't need to remember that the triangle is there because you know the value of Ri, A, and Ro.
Yep.
All right. So and now I give you the values of R1 and R2. R1 I've got is 80 kilo ohms and R2 is 20 kilo ohms. Let's go ahead and analyze this circuit. All right, so let's do the KCL at my output node, which I'm going to call node A. So at my output node A, we have 2 branches associated therewith, assuming that there's nothing connected on the load. So I'm going to do my calculations now along this branch. Okay? So if I'm doing my calculations for current going into the branch and going down the resistor, so I'm going to figure out I3. I3 is Vn minus VO divided by R1. That's the current flowing up through R1. That's going to be equal to the current going along I4 because my arrow is going away from that. So I've got VO minus the voltage at this point, which is A times VP minus Vn divided by RO. So I've got my KCL at node A. Let's do the KCL at node B. At node B, I've shown all my arrows going away, so I'll say the sum is equal to 0. So I've got 1 by 1, so let's do it for Ri. Okay? I have my current going through I1 node is calculated as Vn, that's the voltage at this node, minus Vp divided by Ri. So Vn is the voltage at this node minus Vp divided by Ri. Then I have my current going on path I2. That is Vn divided by R2. And then my final one is the current going up, which we just calculated earlier. Vn minus V0 over R1 is equal to 0. So I've got 2 KCLs. I have now all the information I need to proceed. I can go ahead and calculate VO over Vs by taking these equations and rearranging them to separate out my VO and my Vs. And the reason I can do this in terms of Vs is, what's the relationship between Vs and Vp, Michel?
Oh, they're the same.
Yep, that's right. So anytime I see Vp in here, I substitute in Vs. And so now I have an equation that has VO and that has Vs. And I can organize it and rearrange it to calculate my effective gain. And this is the equation I get. For these values of voltages, resistances, etc., I calculate the gain, and I find it is 4.999975.
Wow, that's really ugly.
Yeah, but now I'm going to show you, by making some assumptions, how we can simplify this. Let's go ahead and assume my gain is infinite. If my gain is infinite, I can do the same thing, but now I get to simplify this equation, and it simplifies to R1 plus R2 over R2, and my gain is just equal to 5.
And that's because there's one term in the numerator that has a and one term in the denominator. That's going to be much bigger than everything else. And once I do that, the RI's and the A's cancel out, so I get R1 plus R2 over R2. That makes sense.
That's right. So we take the numerator, we'll just keep this term, and we'll get rid of the R2, RO. If we take the denominator, we'll just keep this first term and get rid of everything else. The A's cancel, and then you can just get R1 plus R2 over R2.
So it's neat. I mean, again, the ratios of two resistors give us a gain. In this case, it's non-inverting. There's no minus sign to the gain. It's positive. And it's neat to see that, you know, for a very large A, how close it is to the actual expression given the values up at the top left. So we, you know, by the way, those numbers we got obviously from the top left numbers. You can plug them in yourself. It's pretty neat to see. And this gain is 1 million. It's not, you know, it's a reasonable, very reasonable gain. Pretty cool.
Right.
So I think what we're going to wrap up here. What we're going to do in the next module is revisit this to simplify it even further under some conditions, and then give you an overview of lots of different types of op-amp circuits that are useful that everyone should have in sort of their tool grab bag.
That's right. See you next time.
See you.